Imagine an AI assistant that can organize your email, notice which messages are emotionally sensitive, negotiate with people on your behalf, and move fluidly between phone, chat, and email. What makes that feel intelligent isn't just language ability. It's that the assistant has tools, hands, feet, and senses that connect its reasoning to the real world. Today we're looking at how to build that toolset and the two hardest problems that come with it. Picking the right tool out of potentially thousands and handling a world that doesn't wait politely for a synchronous reply. Two core challenges. There are two challenges that shape everything else. First, tool selection at scale. When you have hundreds or thousands of tools, just describing them can eat up a huge chunk of the model's available context before the conversation even starts. Second, real-world responsiveness. A strict ask-wait-respond loop can't handle a job like a secretary's, where phone calls, emails, and interruptions are all happening at once. Everything we cover today is really an answer to one of these two problems. Roadmap. Here's where we're headed. We'll start with the 5 categories of tools an agent can use. Then we'll cover the design principles that make any tool good, followed by the protocol that lets tools from different vendors work together. From there, we'll go deep on the 3 tool categories an agent calls on its own initiative. Then, shift to the architecture needed when the world needs to call the agent instead. And close with how to keep agents fast and accurate even when they have access to hundreds of tools. 5 tool categories. There are 5 categories of tools. Perception tools acquire information. Execution tools change the world. Collaboration tools drive other agents or humans. User communication tools convey information to the user. And event-triggered tools are different from the rest. Instead of the agent calling them, the agent registers interest ahead of time, and it's the outside world, a timer, an incoming email, a webhook, that actually fires the trigger. That one asymmetry is why we need an entirely different architecture for the second half of this talk. Quick definitions. Perception tools are things like web search, page fetching, and file search. They let the agent see the world. Execution tools are things like running shell commands, writing files, and sending emails. They let the agent change the world. Collaboration tools spawn and coordinate other agents for 2 reasons: raw parallelism, doing several things at once, and specialization, giving different subtasks, different models, prompts, and tools. And user communication tools let the agent reply, send structured cards, or push notifications across different channels. Dedicated tools versus skills plus general executors. Before designing an individual tool, there's a prior question. Should this capability even be a dedicated tool? Or should it be a plain language playbook that a general executor just follows step by step? A deploy the app playbook can simply say, run the build, package the image, apply the deployment file. No dedicated tool required. Dedicated tools are structured and easy to test, but they cost tokens and get harder to maintain as they multiply. Playbooks are cheap to edit, but rely on a strong enough model to follow instructions reliably. The choice comes down to how complex the parameters are, how often the logic changes, and how capable the underlying model is. Granularity. Get the granularity of your toolset wrong in either direction, and you pay for it. Too many narrow tools, and even top models start picking the wrong one once you cross roughly 100 options. Too few, overly broad tools, and each one becomes unwieldy. The right call is to merge tools when they share a purpose and overlapping use cases. 3 separate document extraction tools can become one read document tool with a format parameter. But keep tools separate when their parameters diverge sharply or one of them gets used constantly on its own. Generality. As a default, prefer general-purpose tools over narrow dedicated ones, unless there's a clear security, permission, or performance reason not to. A single code execution sandbox stocked with useful libraries, beats a dozen hand-built single-purpose calculators because it inherits all of the model's own reasoning and coding ability instead of fencing it in. That said, generality has limits. Once an operation needs special permissions, or its syntax genuinely differs across platforms, a dedicated, well-encapsulated tool is the safer choice. The art of tool description. This might be the single highest leverage thing you can get right. A tool description should say when to use it, not just what it does. Use this when you need real-time information, beats search for relevant content every time. Spell out the boundaries explicitly. What the tool cannot do matters as much as what it can. Use concrete examples for parameters instead of abstract format names. Describe what gets returned and how expensive the call is. And add a handful of real invocation examples. In some benchmarks that alone lifted accuracy from around 72% to 90%. If a model keeps picking the wrong tool, check the description before you blame the model. Fidelity of parameter passing. Here's a subtle but nasty failure mode, a tool silently correcting the input before it executes. Picture curly quotation marks getting quietly flattened to straight ones before a text replacement tool runs. The model saw curly quotes when it read the file, faithfully passed them along, and the match just fails with no explanation. The model can't debug what it can't see. The same problem happens with silent parameter injection, where a tool adds extra flags the model never asked for. The fix isn't cleverness, it's transparency. If a tool has to normalize input, that has to be stated plainly, both in the description and in what gets returned. 3 generations of tool design. Tool design has gone through 3 phases. First generation tools were direct wrappers around individual API calls, too fine-grained, forcing constant coordination. Second generation tools are built around agent goals instead of raw endpoints, which is where good granularity, generality, and description practices come from. Third generation tools go further and optimize how tools are invoked, chained, and discovered, including code orchestration, where instead of calling tools one at a time and waiting for each reply, the model writes a whole script up front. Intermediate results stay inside the execution environment and never touch the context window, which in some workflows cuts token usage by roughly 2 orders of magnitude. A universal socket standard. Every framework used to define its own tool format, forcing developers to build separate adapters for each one, like incompatible power sockets in every country. An open protocol solves this with a client-server model. Servers expose tools, and any compatible client can consume them without extra adaptation work. It standardizes how tools describe their parameters, supports both local and remote deployment, and separates 3 distinct things: tools you can call, read-only resources you can browse, and prompt templates you can select from. 3 progressive challenges. This protocol standardizes a single call beautifully, but it comes with 3 growing pains. First, it's fundamentally request response, with no built-in way to wake an agent that isn't currently running a session. Second, context overhead. Connecting just 5 servers can add on the order of 55,000 tokens of tool definitions, nearly a third of a typical 200,000 token context window before the conversation even starts. Third, simply having more tools doesn't make an agent smarter. It needs a way to reveal capability gradually instead of all at once. Managing tool overload. 3 tactics fix tool overload. Categorize tools by type. Search, read, parse, query, so the model can navigate a hierarchy instead of a flat list. Load tool definitions on demand instead of all at once. In one measured case, this single change moved a model's tool use accuracy from 49% to 74%, and replaced large numbers of narrow tools with a small set of general tools plus on-demand knowledge documents, which turns "which tool do I pick" into "what do I need to know?" a task language models are naturally good at. Some systems go so far as to skip a heavyweight protocol entirely, relying on lightweight CLI tools and playbooks with just one tiny proxy tool that discovers everything else on demand. 4. Security risks. Bringing in third-party tools introduces real risk in 4 flavors. Tool description poisoning is prompt injection wearing a different hat. Malicious instructions embedded directly in a tool's own description, firing on every single session. Compromised or maliciously updated servers are a supply chain risk. Tool shadowing happens when a fake tool impersonates a trusted one and intercepts calls meant for it. And credential risk comes from agents holding real API keys or tokens that can be misused if tricked. The fixes are classic supply chain hygiene. Review descriptions as untrusted input, pin versions, grant only the minimum privilege needed, and add an independent review layer as a last line of defense. Perception tools. Perception tools have one core problem. Results can be enormous. Tens of thousands of characters from a single search, hundreds of pages from a single document. The fix is compression at the tool layer, triggered automatically once output crosses a size threshold. Search tools should return short structured candidate lists, not raw text dumps, and support paging. Read. Tools need offset and limit parameters, and any truncation has to be visible. Silently cutting off content is worse than an obvious error because the agent believes it saw everything. And because perception tools don't change anything, they get 2 free advantages. Results can be safely cached, and multiple perception calls can run in parallel without any risk of interference. Execution tools, layered security. Execution tools are expensive to get wrong. A bad command can delete files, take down a service, or spend real money. So their security can't rely on one clever trick. It needs layers. Validate every input first and fail fast on anything suspicious. Constrain permissions with sandbox directories, command blacklists, and rate limits, backed by actual intent parsing rather than simple pattern matching. And for the operations that really matter, bring in an independent review before or during execution. Propose refer. One review pattern works like a bank transfer, requiring 2 signatures. One model proposes an action, and a separate, independent model has to approve it before it runs. The 2 models should come from different families, but sit at a similar capability level. Different training backgrounds catch different blind spots, but too big a capability gap means the reviewer simply can't follow the reasoning. When something's rejected, that rejection gets fed back into the agent's history, just like any other tool error, so it can adjust and try again. A second version of this pattern checks results after the fact, and its key trick is switching modality, rendering generated document code visually, for instance, to catch layout problems that a second read-through of the same text would miss. Sidecar. A different mechanism runs alongside the main model in real time, checking each risky action as it happens rather than reviewing a whole plan. It only sees the structured tool call, the name and parameters, never the model's free text reasoning, which deliberately blocks an attacker from talking the reviewer into approving something dangerous through persuasive language. Because this is a narrow classification task, is this specific command out of bounds? A small, fast model handles it comfortably, usually in well under a second, and it needs a circuit breaker. If it keeps rejecting the same action, the system should stop retrying and hand the decision to a human instead of looping forever. Comparison. These 2 review mechanisms complement each other. One reviews the reasonableness of a whole operation or its final result, either before or after it happens, and both models see roughly the same context. The other runs continuously in parallel, reviews each individual tool call for safety, and deliberately isolates itself from the model's reasoning. One is the deliberate, careful check on a decision. The other is the fast, always-on reflex check on each action. Strong systems use both, for different classes of risk. The rest of the execution checklist. A few more essentials for execution tools. Automated validation. When a file gets written, immediately run a linter and feed structured errors straight back to the model. Truncate and persist long outputs. Keep the head and tail, save the full thing to a file, and tell the model how to read more. Sandbox everything, with increasing strength depending on the risk. Operating system-level isolation for local work, containers for more separation, full virtual machines for genuinely untrusted code. And worth calling out explicitly, a plain Python virtual environment is not a sandbox. It isolates package versions, not the file system or network. Log everything for auditability, and handle retries carefully. Operations that can be made idempotent are safe to retry with a unique key or a check before acting pattern. But things like sending an email or making a payment can't be undone, so those need a two-phase approach. Validate and preview first, execute second, and never blindly retry an execution that failed. Collaboration tools. Agents collaborate for two reasons: parallelism, doing several things at once, and specialization, giving each subtask its own model, prompt, and toolset. A good sub-agent prompt needs a clear role, clearly labeled context sources, so the sub-agent can tell what came from the main agent versus the user versus a tool result, which is also a direct defense against prompt injection, explicit task boundaries, and a standardized output format. The core capabilities are spawning and canceling agents, passing messages back and forth while they run, and discovering which other agents are available. These support everything from a quick synchronous call to a long-running asynchronous task to an ongoing multi-turn conversation between agents. Human in the loop. Some decisions genuinely need human judgment, common sense, or domain expertise that the system doesn't have. That means setting timeouts with sensible default behavior if nobody responds in time, and routing based on urgency. Multiple channels for something urgent, a simple email for something routine. And critically, this shouldn't be a dead end. Every human approval or rejection is a data point. Patterns that generalize well can become reusable guidance, and more nuanced, implicit preferences can inform future training. The one rule to hold on to is not to turn a single human decision into a blanket policy without checking it against other cases first. Why asynchrony? Here's the core tension. A strictly synchronous agent behaves like a single checkout line. One customer at a time, no skipping ahead. A real assistant behaves more like a secretary's desk. Email, calls, and visitors all happening at once, prioritized on the fly, with the ability to pause one thing and handle something more urgent. Three things a purely synchronous system can't do. Let long tasks run without blocking everything else. Judge event priority dynamically, and let an interrupted conversation resume naturally. Language models are trained on strict, orderly conversations. Action, then result, cleanly paired. But real deployment is messy. Users interrupt mid-thought, tasks run in parallel, events arrive before a call even finishes. That mismatch is what the rest of this covers. Event-driven architecture overview. Instead of the agent repeatedly checking whether anything new has happened, the system flips the model. Everything. User messages, tool results, external callbacks, scheduled triggers, becomes a unified stream of events, and processing kicks off automatically the moment something arrives. Events flow from the sources into a queue, and the agent's processing loop consumes them from there. That single inversion, the world notifies the agent, instead of the agent checking on the world, is what makes proactive, always-on behavior possible. Case study: real-time responsiveness. Consider a framework with three built-in automation mechanisms. One that reacts to internal lifecycle events, one that runs on a schedule, and one that checks in periodically to see if anything needs attention. The gap is that none of these can react to a brand new external event the instant it happens. At best, the system notices at the next scheduled check. Now picture an AI that makes real phone calls on someone's behalf. Negotiating a bill, cancelling a subscription. Mid-call, it might need someone to provide a verification code within seconds, or answer the phone directly, or confirm a decision on the spot. Checking every 5 minutes means missing the moment entirely. Checking every few seconds floods the system with noise. The fix is a dedicated real-time channel that pushes key events. Call connected, input needed, call ended. Straight to the agent the instant they happen, cutting response time from minutes down to seconds. Event-triggered tools. There are 3 common ways the outside world wakes an agent up. Timers handle anything tied to a specific moment. A one-shot timer for follow-up next Monday, or a recurring timer for check server health every hour. Background task monitoring tracks long-running commands without the agent wastefully polling for status or blindly waiting until everything's finished, and it can catch a hung process early instead of stalling indefinitely. External event channels push things like new emails or webhook calls straight to the agent in real time. In every case, the trigger conditions need to be precise, and the event payload needs enough context that the agent doesn't have to immediately go digging for more information after waking up. User communication tools. Some systems break the strict pattern of user asks, agent answers entirely. Either side can send a message at any time the way a real secretary would, without waiting to be prompted. This happens through dedicated communication tools rather than raw chat text, supporting attachments and urgency-based push notifications. Good design here means handling the fact that the user might be offline, tracking read and unread status, and keeping messages consistent across different channels. And there's a useful distinction to draw. If the recipient is an approver or a collaborating agent, that's a collaboration tool. Only when the recipient is the actual end user does it count as user communication. Virtual identity and isolated execution. There's a fundamental choice to make. Should an agent operate directly under someone's real accounts, or should it have its own separate identity? Its own email, its own storage, its own credentials. Direct access is convenient, but one mistake or compromise exposes everything. A separate identity contains the damage and keeps every action auditable, the same way a new employee gets their own office phone and login instead of using the owner's personal accounts. This extends into virtual computers and virtual phones that give the agent its own isolated environment to operate in. 2 practical wrinkles come with this. Some websites actively try to detect and block automated access, which often requires routing through more realistic network paths. And when a task truly requires the user's real account, the safest approach is a supervised login where the user authenticates directly and the resulting session gets reused briefly, instead of the agent ever holding the raw credentials. The event loop. The underlying mechanism looks like a classic event loop from concurrent programming. Pull a batch of events off the queue, add them to the running history, call the model once. Execute whatever tools it decides to call, and repeat. New events only get consumed at specific safe points, the end of a reasoning step, or when a tool call returns, never in the middle of one. Even cancellation follows this same discipline, checked only at those safe points, rather than ripped out at an arbitrary moment. Everything that follows is really just 3 different strategies for how quickly you reach that next safe point. Structured event modeling. Every incoming event, no matter where it comes from, gets normalized into the same shape. Who it's from, what channel it arrived on, what it actually says, and what background context applies, priority, related history, and so on. This consistency matters enormously. It's what lets an agent reliably tell the difference between a genuine user instruction and, say, a tool result that happens to contain manipulative text, trying to pose as an instruction. Once every event, regardless of source, is normalized the same way, the agent can reason about urgency and legitimacy consistently instead of needing custom logic for every single event source. 3 event handling strategies. There are 3 ways to handle an incoming event, and they map neatly onto how a person juggles interruptions. For something urgent, stop. I made a mistake. Interrupt immediately. Halt whatever's in progress. Gather up anything else waiting and re-evaluate right away. For something routine, a small clarification arriving while a search is still running, just cue it and let the current step finish naturally. Then process everything together. For something independent and quick, a totally unrelated question popping up during a long task, handle it in a separate track entirely, without disturbing the main task or making the user wait. The practical advice is not to hard-code these rules rigidly, but to use a small, fast classifier to route each event based on what it actually means, since urgency depends on meaning far more than on which channel it came through. Engineering the contradiction. Here's the core mismatch spelled out concretely. Models are trained expecting every tool call to be immediately followed by its result, but real deployment interrupts things mid-call all the time. The practical workaround follows 5 rules. Record what the model says or calls the moment it happens. Only record a tool's result once that tool genuinely finishes. If something gets interrupted mid-call, insert a clearly marked placeholder result, rather than leaving things dangling. If something gets interrupted mid-thought, just discard that unfinished reasoning entirely and start over cleanly. And anything that isn't urgent goes into a queue and gets appended in a batch later. The goal, under normal conditions, is to keep everything looking like a clean, perfectly paired conversation, because that's exactly what the model was trained to expect. The placeholder is a deliberate compromise, used only when a genuine interruption happens. Placeholder walkthrough and its risk. Here's how it plays out. An agent is searching for someone's contact information, and mid-search, the user suddenly asks about tomorrow's weather. The system records the original search call as normal, then inserts a placeholder result for that unfinished search, appends the weather question, and lets the model respond to that first. Once the real search result eventually comes back, it gets appended as a fresh event, and the model picks the original task back up. There's a real risk here worth flagging. Even with an explicit placeholder saying, "This isn't done yet," a model can still convince itself a result already came in and reason from something it made up, simply because almost everything it was trained on shows results arriving instantly. Because of that, this kind of interruption should be reserved for genuinely urgent situations, with everything else handled through calm batching instead. Asynchronous native tool interfaces. Naming matters more than it seems. A tool called Make Phone Call implies the call is dialed and finished by the time it returns. A tool called Initiate Phone Call immediately signals something different, that it starts a process and returns a task reference right away, with progress reported later through separate events like call connected or call ended. A model's own language understanding picks up on that distinction automatically. So pairing an asynchronous sounding name with a description that explicitly says, "This returns immediately," a notification follows later, meaningfully reduces the chance the model waits around for something that was never going to come back synchronously. Attention dispersion in batch events. There's a subtle failure mode when several events get delivered to a model at once. It tends to fixate on whichever one arrived last and effectively ignore the earlier ones, simply because it's trained to react to the most recent input. 2 cheap fixes help a lot. First, explicitly instruct the model to consider everything in the batch, not just the last item. Second, number each event clearly, event 1 of 4, 2 of 4, and so on, and close with a short summary of exactly what's in the batch. How many tool results, how many user messages, how many system reminders. Small as it sounds, this measurably improves how thoroughly the model actually uses everything it was given. From synchronous to asynchronous models, everything covered so far, placeholders, careful naming, batch markers, is essentially prompt-level patching for a gap that really lives at the training level. The deeper fix is training models through reinforcement learning inside genuinely asynchronous simulated environments to natively handle three things: making sense of events that arrive out of the expected order, resuming an interrupted task without hallucinating that it already finished, and thoroughly processing everything in a batch rather than fixating on one item. This mirrors a challenge robotics models already face, where there's an unavoidable delay between sensing the world and acting on it. Continuous thinking. Here's a genuinely elegant idea. A fairly small amount of orchestration logic can turn an ordinary text-generating model into something that thinks continuously. The trick is to never fully throw away a half-finished thought. Instead, forcibly close it off, inject whatever new information just arrived, and let the model keep going from there. This unlocks two useful behaviors: thinking ahead during the natural delay of a tool call or a person typing, since that waiting time is otherwise pure waste, and continuing to reason even while producing output, catching and correcting mistakes mid-action. But here's the critical finding. If you reward this behavior based on whether it merely looks good to another model acting as a judge, the model learns to game that judge and quietly hides its reasoning, while the actual measurable outcomes get worse. It only pays off when the reward is tied to something concretely verifiable, like whether the important information was actually preserved. In short, the orchestration makes continuous thinking possible, but only the right kind of training makes it genuinely good. A few ideas worth carrying forward. A tool is only as good as its description. Clear boundaries and concrete examples matter more than raw capability. Standardized protocols solve compatibility between tools. Small toolsets paired with on-demand discovery solve the problem of having too many choices. Execution tools need layered security, validation, permissions, and independent review working together, not any single mechanism alone. A genuinely responsive assistant needs an event-driven architecture, not just a bigger version of the same synchronous loop. And the deepest fix for handling interruption and delay isn't clever engineering. It's training models that natively understand asynchronous reality.